So here we are in lecture 2, talking about the real ideal paradigm. And let me remind you where we were. So our first example is concerned with the NCPA security of a symmetric encryption scheme built from randomness and a pseudorandom function. And so let's review, and maybe you've been thinking about some of these things and questions have come up, so feel free to ask them as we go through the review. So we have, so these are in EasyCrypt. We have types of keys, encryption keys, which have k-len bits, a tunable parameter. We have a type of plain text, which has text-len bits, and then we have ciphertexts, which are scheme specific, but for the particular scheme we're looking at, we know what that is. We'll get to that in a few minutes. An encryption scheme is an implementation of these 3 procedures. You can think methods, and it's supposed to be stateless, so not have any module level state, key generation, encryption using a key, and then decryption of a ciphertext using the same key. Those are supposed to cancel out. The way that we define NCPA security is using something called an encryption oracle, which provides these 4 procedures. And I'm going to show you the standard one in a second, so we can go over what they do. So this encryption oracle is built out of an encryption scheme. Take any scheme you like, good or bad, plug it in here, and it gets used by these procedures. It has 3 module level variables, a key, and 2 counters, and it generates a key using the scheme, whatever keygen of the encryption scheme does. That's what's stored in key. The counters are initialized to 0. Enc-pre encrypts a plain text using this key. The key that the encryption oracle knows, but for instance, the adversary doesn't directly know. So it checks if the counter is still less than the limit for limit pre. If so, it increments the counter and then does encryption using this key. Otherwise, we get this dummy result. As someone pointed out, it really could be anything. It could even be random. This constant limit pre is something that the adversary knows also, and so it can predict that it's not going to get any good results after some point. GENC is what the game in CPA game is using. It encrypts using the key with no limit. Enc post is like enc pre, except that the counter is counter post and the limit is limit post. And then what's an adversary against the scheme? An attacker of the scheme. It's something that has access to some encryption oracle, like the standard one that we just saw. We can give it access to an encryption oracle. It has 2 procedures, one for choosing a pair of plain texts. While it does that, it can call enc-pre as many times as it likes, but of course it won't get interesting results after it reaches the limit. And then guess is something where it's given a ciphertext, which will have been based on, it'll be either the encryption of X1 or X2, depending upon whether the game's coin flipped up heads or tails, true or false. And then it tries to guess what this Boolean is, what the game's, how the game's coin came up, and return that guess. While it's doing that, it can call enc-post. And then here was the NCPA game. So we connect, we build the standard encryption oracle out of the encryption scheme, which is a parameter to the game. And then we give the adversary access to that standard encryption oracle. That's what A is. And then the main procedure, it initializes the encryption oracle. It invites the adversary to choose its pair of plain texts, X1 and X2. And remember, while it does that, it can do encryption using the key that was created by this initialization, which it doesn't know. So it can experiment with that very same key via calls to enc-pre. The game then flips a coin. If B comes up true, then X1 is encrypted, otherwise X2 is encrypted using GENC, and then this ciphertext is given to the adversary. The adversary then is trying to return a Boolean that's the same as B. So it wins if it manages to take information about the ciphertext of X1 or X2 and think, oh, okay, that must have come from X1, therefore I should say B, or if it's X2, I should say B prime. Or sorry, I should say true. In that case, I should say false otherwise. So that's the NCPA game. Any questions so far? Okay. So what we're trying to do is prove for a particular scheme, which we'll see the one we're working with again in a minute, that the absolute value of the difference between the probability that the adversary wins the game, correctly guesses B, and a half is less than or equal to some bound. And the bound is going to, as we'll see, involve the adversary. That might be counterintuitive, but we'll see why. But it's also going to be a function of the number of bits in a text value, text len, and the limits, limit pre and limit post. It may or may not be clear to you yet why this might be so, but we'll get there. And well, right, ideally, we would like this upper bound to be 0 to be able to prove that the adversary can't do better than half the time. Can't win better than half the time. That turns out not to be possible, but we want this ideally to be as small as we can. Okay, so how, for our particular scheme, we're building it out of a pseudo-random function, which we're modeling as an operator, just a function that takes in a key. Once you give it a key, then it's determining a function from text to text. So there are 2 to the key len, different keys, so there are at most 2 to the key len different functions that are determined by F. Okay? And then we also need distributions on text and key. So, and these are uniform distributions. So choosing a text value is something that each of the 2 to the text len different text values are equally likely to be picked, and similarly for keys. Right, okay, so how did we say when a PRF is good? We do it using a very simple case of the real ideal paradigm. So this is really our first example in the wild, if you like. So a random function module has 2 procedures, initialization and a procedure of transforming a text value to another text value. And we have 2 implementations. There's one that uses the PRF, uses the F. So init just generates a key and stores it as a module level variable. F uses F of key to transform X into Y and then returns that. So whatever F does for the particular key that was chosen, that's what this does. And so once initialization happens, the key is then fixed, and we can call this as many times as we like. The other one, though, is a dynamically created random map. So initially, we have a map from text to text, a finite map. Initially, we make it empty. Each time F is called with X, if it's already known by the map, then we just look up the value that the map gives X and return that. Otherwise, we generate a random answer and then update the table to say that X gets sent to Y. And so all of the 2 to the text len, 2 to the text len, different finite maps from text to text are all possible. We start out with empty. Each time we call F, we're getting one step closer to knowing which one we have. We don't have to call it on all text values, of course, but if we did, then one of those very many different text maps would be what we would get. Okay. And then a random function adversary, which is different, but we'll see how they're connected to the symmetric encryption adversary, is given access to the F function, but not initialization. It can't reinitialize the random function, and it returns a Boolean. And you can think what it's trying to do, and well, we can see this in the random function game. So we give the random function game a random function and a random function adversary. We connect the adversary to the random function. We initialize the random function. In these standard cases, that's either picking the PRF key or it's initializing the text map to be empty. And then we let the adversary experiment with the F procedure to its heart's content. And it returns a Boolean, which is returned as the result of the game. And so here, we should be thinking that the random function adversary, if we anthropomorphize, is trying to guess whether it's in the real world, the PRF, or the ideal world, the true random function. So that's what's in its head, and it's trying to figure it out, and it's trying to return true with different probabilities. So if it was in a perfect world, it could say, haha, this is the PRF, I'll return true. Aha, this is the true random function, I'll return false. That would be like perfect, but of course it's not generally going to be able to do that. And in fact, to say that a PRF is good, we want the absolute value of the probabilities that the random function game returns true, so the random function adversary returns true, is small. But this quantity here, is it small? Well, it depends upon a bunch of things. It depends upon the quality of F, the number of bits in a key, but also about how we constrain RFA. So as we saw last time, if you let it do as much computation as it wants, it can tell the difference between these two worlds. So we're assuming that we constrain it when we think about this bound, that we constrain it in some way.
Can you explain the difference again between the real random function and the true random function?
Yeah, I'll go back for a second. So the real one is just based, it picks a key, and then when an X comes in, F of key, right, is a transformer on text values that's determined by key, and so we simply return that. But the ideal one builds dynamically a map. Each time it's called, which starts out at being empty, each time it's called with a text value, it says, does this map already have the answer? In which case it just looks it up. Otherwise, it creates a random result and updates the map.
Okay, so in the one it's giving like a random text value, like basically sampled from all the possible text values.
Yes.
And the other one is taking one of the keys and transforming it somehow into one of the text values.
Yes, that's right. So in the PRF here, the key, the random function, or the PRF key is picked up front. And then once we've done that, this F of key, so it's curried, is now a fixed function. And you call it, and it gives you, with a text value, it gives you a text value back.
Okay, so the pseudo-random function is using one fixed randomness for the whole thing, whereas the true random function is using new randomness for every.
Yeah, absolutely, that's right. Okay, good question. And so what we're going to be doing is treating this term here for a particular random function adversary, which in fact will be built out of the real symmetric encryption adversary, treating this as a formal term. And is it really small? It depends upon these assumptions. But in the EasyCrypt proof, we don't care, actually. So we'll be able to do a proof that is correct, that is valid, even if it turns out that the bound with the wrong assumptions, if F is bad, F is somehow predictable, then the bound might not actually be good, but it doesn't matter in terms of the formal proof, and we'll see how that works. Okay, so our particular encryption scheme, is using bitwise exclusive OR on text values. Ciphertexts are pairs of text values, which probably seemed a little obscure. Key generation just generates a PRF key. It's the same, so the symmetric encryption keys and PRF keys are the same. What does encryption do? It generates a random text value, and it returns the pair of U, that random text value. And what we get by taking F of the key that we're encrypting with and using that to transform U into a text value and then exclusive ORing, so bitwise exclusive ORing. And then when we decrypt, we take this thing apart, we recover the U, which we stored as part of the ciphertext, and then take the second part and exclusive OR it with FKU, and the two occurrences of FKU just cancel out because that's how exclusive OR works. So that's what this slide said. Okay, so that's where we were. Yes?
Why does the encryption function return K also, the random number? So why does it return U also?
Yeah, because if you think about it, when you try to do decryption, suppose we just had the V, then we can't actually figure out what to exclusive OR with. We need the U as well. That's a good question. Uh-huh.
So I have two, I guess, somewhat related questions. So is F a function that is assumed to be known to the attacker?
Yes.
And then related to this, so how do we bound the number of computations that the attacker does? Because it seems like we're counting the number of function calls that the attacker does to the encryption decryption oracle, but the attacker could somehow, given that F is known, will call F unboundedly often.
Yeah, that's right. And so that's what I was trying to talk about, that outside of the formal proof, we, in our head, we will look at the bound and we will think, well, we only really care about this theorem that we're working towards if the symmetric encryption adversary is well behaved, that it doesn't run, too many steps. But that's not actually something that we're formally tracking in EasyCrypt. And we'll see how this works. So it's a perfect question. Kind of the beauty of the EasyCrypt approach is that we don't have to treat that formally. But let's go on a little bit and we'll see how that plays out. Okay, right. Okay, so let's think about if we were the attack, the symmetric encryption adversary, how would we attack this scheme? There are a couple ways. One is when we're being asked to pick our pair of plain texts, and we can call enc_pre, we can call it repeatedly on the all 0 bit string. So we get a whole bunch of things like pairs like this, some UI, and then we're encrypting text 0 with this. But of course, the text 0 just drops out. So we have a bunch of things that look like this, some random UI and F key UI, like that. And so we build up this table, and we can only call enc_pre limit pre times and get something interesting here. But we could, for instance, we could exhaust that entire limit. And so we have this table. And then when we give the game x1 and x2, the game is encrypting one of them. We don't know which one. That's what we're trying to figure out. But it might happen that when it does the encryption, that the U that it picks just happens to be one of the ones that already came up in our experimentation. So we have a table of these things. Each of these UIs was produced randomly, independently. But when the game does the encryption, it's also via the encryption oracle, some random U is being picked, and then either xj is either x1 or x2, depending upon whether B is true or false in the game. So it's doing this. But this UI might be one of the ones that we already discovered in our experimentation using ENC-PRE. And if that happens, then our heart, leaps with joy if we're the adversary, because what we do is we take this here, the second part of the ciphertext that we got back from the game there, and then we take f of key of ui, which we got from this table. The ui's happen to collide, these cancel out, and we recover the xj, and so we can figure out whether that's x1 or x2 and whether we should return true or false. So if we're lucky, right, in our experimentation with ENC-PRE, we just happen to get in one of the ciphertexts, have the left side be the same left side that happened randomly to be created when the game did the encryption. You can do the same thing with ENC-POST, but there's one completely or different kind of thing that you could do. The adversary can, again, encrypt text 0 over and over again, getting this table. But then, as the person over here was saying, because the adversary can experiment with capital F directly, it's just this public function anyone can use. The adversary can use it. And so we have a table of UIs and then F key of UIs. And so it can then shop around trying to find a key that produces the same behavior, the same input-output behavior. And if it can do that, well, then there's a good chance that it has the key that will actually decrypt the real key. And so it could actually decrypt the ciphertext. And so it's a subtly different way of doing an attack. Okay, so this just informs how what we might expect the form of the theorem to be. So what's the upper bound going to be a function of? It's going to be a function of the ability of a random function adversary constructed from the real symmetric encryption adversary to differentiate between the PRF and the true random function. And we'll see why, but the intuition here is this is going to let us switch in our proof from using F, which we don't understand, to using true randomness, which we have a complete model for. And so that's why that's going to be part of the upper bound. It'll also be a function of the number of bits in a text value and the limits, limit pre and limit post. So this bit is, we saw that the bigger those limits are, the better we can do as an adversary. This bit is kind of technical, but you'll see why shortly. Right. And why don't we have to explicitly involve keylen? Well, because we're already talking about the ability of the constructed adversary to tell the PRF from the TRF. If the key is tiny, then it's going to be easy for it to do that. Okay, so what's our game plan? We're going to be using in our proof what's called the sequence of games or game hopping style. How many people have heard about this? Yeah, okay, a smattering of people. We're going to be connecting a real game with an ideal game and via a sequence of intermediate games. Each of these games is parameterized by the adversary. Each game has a main procedure returning a Boolean. And what we want to do is prove an upper bound on the absolute value of the probabilities that true is returned by these two games. Uh-huh. Not that work well in EasyCrypt. So crypto theory people, I don't pretend to understand all of their proofs. Sometimes they do things and I scratch my head and I think, I'm not sure why this is this is valid. So this is the way that we have to do it in EasyCrypt. Right. So we want to bound the distance between the probabilities that the real and ideal games return true.
For the sequence of games approach, I'm not familiar with this. Do we think of each edge like a reduction?
Well, I'll explain. So these are intermediate games. And then what we can do is this kind of thing. So from R to G1, suppose the upper bound is B1. And then we go from G1 to G2 and G2 to G3 and G3 eventually to the ideal game. You have all these bounds. Then going all the way from R, from real to ideal, the bound is going to be, what do we do to these things? Yeah, we sum them, fortunately, like that. And I mean, this is an upper bound. It's not tight. You might hope that like some of these things would cancel out, but anyways, this is the best that we can do. So each step has a penalty. We sum all the penalties is the way to think about it. And well, why does this work? It works because of the triangular inequality, that the absolute value of x minus y is less than or equal to the absolute value of x minus c, x minus y plus y minus c. So these have to be the same, and then you can go from x to z. So that's what justifies the math on the previous slide. So what's our real game? Well, right. Okay. What does this have to do with this form, though? You might be wondering. Well, this thing here is our real game. But what's the ideal game? Well, the ideal game should be something that the adversary wins exactly half the time for this to work out. And so we can use a sequence of games to connect the real game to an ideal game that, as I just said, the adversary wins precisely half the time. So this is then going to be our second example of the real ideal paradigm, again, without a simulator. So in examples 2 and 3, we'll work with simulation-based security. But the question is, well, okay, what is the ideal game? And here is the general way that we think about, the overall bound, is the sum of the penalties of each of the steps. So what's this ideal game? How do you, in general, do you think about that often? Well, you start with the real game and you make a series of simplifications, hoping to step more and more and more in the ideal direction. Maybe you know what your destination is at the beginning, but sometimes we just don't. And so some simplifications use code rewriting, like a bunch of inlining and changes that don't change the behavior of the program. And there, the bound is 0 because there's no cost. There's no penalty for doing that. Some simplifications use cryptographic reductions, as someone was asking about, maybe over here. Like a reduction to the security of pseudorandom functions, we'll see that. And there, the upper bound involves a constructed adversary for the security game of the reduction. We'll see that in practice. The other main possibility is what's called up-to-bad reasoning. And that means that the transition from one bit of code to another is going to be valid unless something unfortunate happens. And that's the bad event. And what we do as the penalty is we upper bound the probability that the bad event happens. So if there's some probabilistic thing which is not likely to happen, and if we assume it doesn't happen, then we can simplify the code, then we can do a step like that. And we're going to be using, in fact, all 3 of these techniques in our proof. Okay, so here's the high-level structure. So we are going to enter what's called a section and then declare av to be some black box adversary that implements this interface that doesn't interfere with the global state of any of these other things that are here. So the encryption oracle, the way the standard encryption oracle, the PRF and the TRF, they all have state. So we're assuming here av can't look inside their state. And it's a symmetric thing, actually, and vice versa. And there's something more here, but I haven't introduced that yet. So pedagogically, it would be confusing, but in the actual proof, this extra thing that's in red, we've already defined. So we'll define it later, and then we'll imagine that we pushed it back here. And then we're also, for technical reasons, we're having to assume that the adversaries choose and guess procedures always terminate, no matter what inputs they're given, with probability 1. And this is assuming that, that the encryption oracles enc pre and enc post, which they call, behave similarly. And so, so assuming that, so we're requiring that the adversary be well behaved, that its procedures always terminate. And these, this declaration and these assumptions, when we state lemmas involving them inside the section, when we exit the section, well, if we have a non-local lemma, then the lemma will be implicitly quantified by the adversary under the assumption that these things, assumptions are true. And so I'll show you how that works at the end. But in the middle of the section, we can just think, well, av is some adversary that has these nice properties. Okay, so step 1. What we're going to do is we're going to replace the PRF with the TRF. The pseudorandom function based random function module with the one that is based on randomness, because that's going to give us a handle for doing the rest of the proof. And we do that because we have an exact model for how the TRF works. We're going to do more in this step. We're going to inline the encryption scheme into a new kind of encryption oracle called EORF, an encryption oracle that's parameterized by a random function. And we're going to instrument this encryption oracle to detect two kinds of clashes. And that's in preparation for steps 2 and 3. So this is what it looks like. So the encryption oracle, remember, originally was based on an encryption scheme, the standard one. This one is parameterized by some random function, PRF, TRF, or something else, conceivably. Inside, we have the old things like the counters, but we also have all these things in red. And let me explain them as I go along. So init now doesn't pick a key. It initializes the random function. But if it's the PRF, then that's picking a key. So it initializes the random function. These things, so this is a finite set, which is being initialized of text values, being initialized to be empty. These clashes are being set to false. Ignore that for a second. I'll explain these as I go along. So in enc pre, what do we have? Well, partly we have the inlining of encryption. So we're picking this random U. We're recording it in this finite set imps pre. So each time we pick a U randomly, we're keeping track of that in this finite set. Then what we're doing is we're running it through the random function, getting a V, and then the ciphertext is U paired with exclusive ORing the plain text X with V. And so this, if you imagine that RF is the PRF, this is doing exactly what we did already, except that we've inlined it. But we're allowed to switch RF to be the true random function, in which case we're picking V, well, according to real randomness. So that's n right. So the size of imps pre, because there's this limit, it can never be bigger than limit pre. That's important. The game's encryption. So here we're inlining again. We pick the random U. If U happens to be one of the ones that already came up and was recorded here, then we mark this Boolean to say, oh, this bad thing happened. A clash with the U's in pre just happened. We hope that won't happen. But then what we do here is exactly what we would have done anyways, except that we're also recording this U as genc imp. So we're keeping track of that as well. That's another one of these new module level variables. But otherwise, this is just the inlining as before. And then enc post is similar, except this time, when we pick the random U, if U happens to be the one that was used here, used by the game's encryption, that's when we say that there was a clash. And maybe you can see that these clashes have to do with those ways of attacking the scheme that I talked about before. So if, just to say it one more time, if the U that the game is using for encryption happens to be one of the ones that came up in the calls to enc pre, then we say, oh, something bad happened, but we don't do anything different yet. And similarly here, if the U that's used in enc post at one of its calls conflicts with the one that was used for the official encryption, we mark that there was a problem. Yes?
So are we assuming there has to be a one-to-one correspondence between the U's and the
No, we're not. Yeah, so, I mean, each time we do encryption, then it's involving sampling a random U. They're all independent. They might be the same, they might not be. Okay? So far, all we've done, we did a bunch of inlining. This thing is based on a random function now, rather than an encryption oracle. But if the random function is the PRF, then we get exactly what we had before. But we've got all this instrumentation that's keeping track of stuff. In particular, it's keeping track of these clashes, but not doing anything different. So far, that's crucial. And then, right. So now we can make a game out of EORF that is just like the NCPA game, except now we're connecting EORF with some random function, the parameter to the game, and then giving that to the adversary. This is exactly as it was before. And so what that means is that now we can go from our real NCPA game to G1 of PRF. So if we plug in the pseudo-random function here, then these do exactly the same thing. And so we get to prove that these probabilities are exactly the same. There's no penalty at all for this step. So all we've done when we get to here is we now have, are using this game G1, which is parameterized by an RF, but so far it's just the PRF, like that. So we get to here. But now what we'd like to do, yes?
Just a quick question. So when we instantiate G1 with the pseudo-random function, is it trivial for EasyCrypt to prove that basically our additional instrumentation doesn't give the adversary more capabilities? Or is it something we have to somehow manually?
Yeah, so I should have said, these are highly manual proofs, but on the other hand, that's a very easy proof to do. So the code is it's very simple to bridge the gap between here and here, but you have to do it using tactics. You have to do it kind of manually. Yeah, sorry. So good question. I mean, there's a lot of manual stuff, but as the manual stuff goes, this is really easy. Okay, so now what we'd really like to do is go from PRF, G1 of PRF, to G1 of TRF. We're set up because G1 is parameterized by a random function. We can talk about this. How do we do that? Well, we have to construct a module av to RFA. That's that thing in red that I mentioned before that takes in an adversary and takes in a random function and then has a main procedure and whatever else it needs. But the way to think about this is that if it's like a curried, despite the fact that the syntax doesn't kind of look that way, if you call av to RFA with just a symmetric encryption adversary, it's left waiting for a random function and then has a main procedure that returns bool. So in other words, it's giving us a random function adversary. And what is this thing going to be? Let me explain how we should think about this. So what we want is to be able to prove a perfect equivalence between G1 of some RF that doesn't interfere with anything that's relevant, and the random function game, which is this applied to RF, and a constructed random function adversary that is built out of the real adversary. And the way to think of it is really simple, that this random function game is initializing the random function, and then it's giving this thing here the chance to experiment with it. What is G1 doing? Well, G1 is initializing the random function as well, and then it's doing all the stuff that we saw in G1. So basically, all we have to do is take what G1 of RF did apart from the initialization and stick it into av to RFA. And so this is how it goes. So this is av to RFA, and so it takes in a symmetric encryption adversary, it takes in a random function, and it doesn't initialize the random function. We're going to be able to take out all the instrumentation here because it's not relevant and it's distracting. But then this is all just like what we had before, minus the instrumentation. So is this, so is that. And then the main procedure does what G1 does, except now it's using this locally defined encryption oracle, so EO here. And the only thing that's different, right, is that initializing that encryption oracle doesn't initialize the random function. That happens in the random function game. So the cool thing is that then we can go from here to here completely generically. So G1 of RF to the random function game of RF and the constructed adversary. Again, this thing is doing just what G1 of RF is doing, except for the random function initialization, which is happening in the random function game. So we already were able to go from here to here, but this lets us do for RF being PRF or TRF, we can go from here to here. So we've gone from here all the way to there. We can go from here to there, plugging in TRF instead. And so then what we have is that if we do the absolute value of this minus that, that's going to be equal to the absolute value of this minus that. In other words, it's going to look like that. And so you could write that, of course, as less than or equals to, but it's an equality. So going all the way from our real game to G1 of TRF, the upper bound, which is actually an equality, is what? It's the ability of this constructed adversary for random functions to tell PRF and TRF apart. Your head might be swimming slightly, but what we've done at this point is we've managed to get rid of the pesky PRF, which we don't understand. You know, it's some function. Maybe it works nicely, maybe it doesn't. But now we've gotten onto the point where we're working with TRF, which is this thing that we understand completely. We have a probabilistic model for it. Yes? Sorry, I didn't hear the question.
Is NCPA the game, NCPA game, or is it G1?
Well, right. I mean, we got, so we can go previously, we did this, and then we can do this by an instance of that. Yes.
So I'm a bit confused. So my understanding of this adversary to RFA additional step that we did was that this was a sort of a helpful rewriting that was going to make the proof easier. But now in the presentation of the bound, it seems like we sort of maybe did something philosophically different that's going to help us. So at what point in this rewriting have we just been doing sort of cleanup, and at what point have we sort of made a philosophical jump?
Yeah, I mean, I think there is a philosophical jump that these two things here, because of how we define this, they do the same thing. It's just that we've massaged where the random function initialization happens. But because this thing now involves this random function game, then when we make the transition to here and we look at this, we can think of this as part of a security bound. And this is telling us how well does this thing tell a PRF from a TRF. And so we made a step where we wanted to get rid of the PRF because we don't understand it and get to this true randomness. The cost of that step is this bound here, which might be small, might be big. I mean, again, you know, how much work does AV to RFA do? Well, it's really a function of how much AV does, because that's what's driving it. And so if we assume that the real symmetric encryption adversary is kind of well behaved, then maybe we think that this bound is okay. Yes.
Yeah, sorry, I think just like a clarification of that question. So like NCPA and G1 and GRF are all just different games, right? And
Yes.
you're comparing different games, like the probability of things happening with different inputs to different games.
Yes.
Like that's what's happening.
Yep. That's this whole sequence of games approach is you connect a bunch of Boolean and returning games that are parameterized by an adversary.
And you're building these games in service of these proof steps.
Yes.
Right? Like the intermediate games on their own don't really, you wouldn't use them.
Yes. Okay. Right. So now we go on to step 2. And in step 2, we're going to make use of up to bad reasoning to transition to a game that's called EOO for oblivious. And I'll explain how this works. So now we don't need imps pre anymore because we have the domain of the true random function. So we can just think about that. That's what we're initializing. We don't need, we can forget about random functions as a parameter. And right, so here we're just using TRF now. And the domain, size of the domain is going to be bounded by limit pre. But the key step here is that we are going to, when we do the encryption, the game's encryption, we're going to generate a random V, and we're going to update the map of the true random function to send U to V, ignoring the fact that actually, well, U might already be in the domain of the map, in which case V would have been what we get by looking up the value in the map. So we're doing something here where we're saying, well, if this clash is not set, if U is not in the domain of the map, then this is a sound transformation. We just generate a random V and give that as the value of U in the map, and that's what we use to exclusive OR with the plain text, so that's all great. But in the unlikely event that this U had already come up in enc calls to enc then of course this isn't sound. But that's how up-to-bad reasoning works. So this is taking us one step in a direction we want to go. What we exclusive OR X with when doing the encryption is always fresh. This is great for us, but this isn't always valid, right? It's when is it not valid? Exactly when this clash pre has been set. And so the rest of this is just, well, we're using TRF, otherwise it's the same. So now, what can we do? Well, we can prove this lemma so it's a PRHL, a probabilistic relational horologic lemma. And the interesting thing about this in the post condition, it's saying when you run G1 of TRF or G2, G2 is the one where we've made this unsound change, that after you run these things, clash pre has either happened in both or in none, because we instrumented for this clash from the get-go. So either we had a clash in one or in not. And then we're saying, well, if the clash did not happen in either, in one, but in either, then actually the results end up being the same, probabilistically the same. So, as long as the clash doesn't happen, everything is great. If it did happen, well, then we don't know anything at all. And then we can upper bound the probability that the clash does happen to be what? Well, to be limit over 2 to the text len. And that's because, if we go back for a second, how big can this get? So this is called up, up to limit pre times. It's generating, right, it's calling trf.f with U, and so the map is having stuff added to it. So the domain of the map is going to be at most limit pre, which is why the probability that the bad event happens is upper bounded by that. And then the nice thing is that you can take this proof and that proof and combine them to say that the absolute value of this minus that from G1 of TRF to G2 is upper bounded by the probability that the bad event happened. And if we put this together with what we had before, so now we can go all the way from here to there, and our overall upper bound is the one that we had before for the PRF to TRF step, plus this new step. So we've made a little progress. Now we're on to this G2, and our bound has gotten worse, but that's okay. Okay, so then the next step, we're going to go on to an encryption oracle called EOI, I for independent. And so let's see how that works. So we don't need clash pre anymore. No changes here. Here, what are we doing? We're remembering the U. We're generating a random V. We're using it to exclusive OR with the X. But we're not updating the map at all, which is great for us. But of course, well, what's the problem here? The problem is that in enc post, if the U that's picked happens to be the one that was used and saved here, well, then we've got a divergence again. And more than that, at this point, because we're not updating this map, after this point, the map on GIMP in the two games is just going to be almost always different, because originally we were picking a random V and updating U. Here we're not. But we're never, unless this bad event happens here, we'll never even notice that. That's the way to think about it. So the cool thing about this is that we're picking a random V and we're only using it ever once. And so this is going to be crucial in the step after this. So this time, it's an up to bad step. We can prove that either the clash post happens in one, in both, or in neither. And if the clash doesn't happen, then again, we don't notice this optimization that we did, and everything is great. But there's some interesting things to finesse in the proof. The maps become different, but we can prove that that doesn't matter. We need to, here, to do up to bad reasoning, we need to assume that the adversary's guess procedure is lossless, always returns with probability 1, no matter its input. The really subtle thing, though, is that to do this, what's the probability that the bad event happens? It should be limit post over 2 to the text len. Well, why? Let's back up for a second. So if we look at what's going on, whoops, when guess is called, it can call enc post. And each call of enc post has a 1 over 2 to the text len chance of causing this clash. And so we use something that's called the failure event lemma, FEL, to upper bound that probability. So we can have at most limit post interesting calls of enc post. After that, nothing, just a default result is returned. And so that lets us bound this probability. Each call has this probability. So we can say that limit post times that, or this is the probability. Okay, so then now putting it all together, we've got this, but of course we can regroup that to look like that. And in fact, this is going to be our final bound, but we're not done yet. So we're on to this G3 main. What do we want to do to that next? We want to do what's called a one-time pad step. So here, so EON, N for whoops, N for no, so is looking simpler. We've gotten rid of all of the instrumentation, and pre looks like it did before, minus all the stuff we took out. GENC, though, we're making one more step here. So before we were doing this, generating a random V, exclusive ORing the plain text X with it and pairing it with U. Now we're just putting V there. And so now we're not even referring to the X, right? Here's this X, it's being encrypted by the game, but now the right side of the ciphertext is just this random V, which is great. And it turns out there is no cost to this. I'll explain why in a second. The C is independent from X. Consequently, what's different here is this, that when GENC is called, we flipped a coin. Before we were encrypting X1 or X2, but now it's not relevant anymore that the input to GENC is ignored, so we can just call this with the all zero text string. So this is great. How does this proof work? It's a one-time pad argument. It's sort of like what I showed you on the first day, that we can go from this to that using the RAND tactic that I showed you. And the reason that this works is that V is only being used here. It's not being used anywhere else. It's not being put into the map. That's absolutely crucial. But also, well, exclusive OR is well behaved. So we can have this isomorphism on the distribution like we did before. So now we get on to here. That's where G4 is where we've come to. And right, actually, I didn't say it out loud, but let me say it if I back up. This G4 is now finally our ideal game. And because what? Because you can actually figure out here that B and B prime are going to have to be independent. So the adversary is going to win this exactly half the time. And so let's see. Right. So to prove that the adversary wins exactly half the time, we can take this sequence here, and we can choose B at the very end, like that. And so at this point, B prime is this fixed thing. And so we can prove that B and B prime end up being the same exactly half the time. OK. So putting it all together, well, this is our final lemma. The other lemmas were local. They involved local modules. I didn't emphasize that fact, but now this is something where we end the section. Then EasyCrypt adds this quantification on AV and these assumptions about AV, but then otherwise we have our bound that was as before. And do we like it? Well, we can make assumptions about the PRF and the efficiency of AV. So maybe we think this part of the bound is OK, but this part we can tune. We can make text-len be big. We can make the limits be small enough so we can actually calculate that part of the bound. If we remove these restrictions, then the adversary could mess with the global state of these things and a bunch of things would break. So we have to make that assumption, but it's completely natural. The losslessness assumptions would break things as well. When we're trying to prove that G4 returns true exactly half the time, if the adversary could like not return, then that wouldn't be true. But then maybe the big thing to pay attention to here is, why did we do this sequence of games the way that we did? We switched to a true random function, so eventually we could do the one-time path step. So initially we get to here, so we're picking this random V, which we understand. We can predict how that works, and then we could make the step where we didn't even update the map, and then we can make the step where we don't even involve X as part of the ciphertext. And we couldn't do any of that if we stayed with the PRF. And so that's why the structure of this proof is the way that it is. So questions? OK. So let's see, how long do I have? 15 minutes. Let me just set the stage. I mean, there's just a little bit about this next example, but let's see if we can get through this so that you can think about this before the next lecture. So example 2 is about a protocol, a 3-party protocol called private count retrieval. We're going to be proving what's called honest but curious or semi-honest security against each of the 3 protocol parties. So the way to think about this is, suppose the adversary lives inside one of these protocol parties. It's not allowed to change how the protocol works, but it's allowed to try to learn more than it should be able to. We want to prove that it can't. That's what security is going to be. So there's a 3-party protocol. There's a server that holds a database, a client that makes queries about the database, and an untrusted third party. Untrusted is key, crucial here. We're not trusting any of these three parties. That mediates between the server and the client. A database is ridiculously simple. It's just a list of elements. And a query is a query, a request to know how many times some particular element appears in this list. So it's a very, very simple thing. Let me give you an example. If this is the database and we query 0, well, it appears twice. If we query 4, it appears once. If we query 3, it appears no times. So that's all we're doing here. A database is a list of elements. A query is an element. The client is asking, how many times does this element appear in this database that I don't know anything about?
So in this example, does the adversary only corrupt one of the parties?
Yeah, so let me go on and explain this. Okay, so we want informally that the client only learns the counts for its queries, not anything else about the database, and will limit how many queries it can make. The server to learn nothing about the queries made by the client other than for kind of technical modeling reasons, the number of queries. We'll come back to that. The third party, the TP, to learn nothing about the database and queries other than certain patterns. I'll explain what that means more precisely. The protocol makes use of hashing. And the thing that we want from hashing is it should be very unlikely that hashing different inputs results in the same bit strings. And it should be hard, given a hash result, to find something that hashes to it. We could use one of the SHA functions, SHA-3, for instance, for hashing. But we're going to be instead working in this pure world where we can use what's called a random oracle. This is just like the true random function, except it's something that the adversary also has access to. So if you think about the symmetric encryption example, the adversary didn't directly have access to it. But here, we're going to give the adversary, as well as the protocol parties, the ability to query this random oracle, this true random function. Okay, so here's how the protocol works. We've got the three parties. We've got a driver called main. We have an environment, which is the rest of the world, which is providing the database and the queries and consuming the results. And so what does the protocol do? It first invites the server to generate a secret, which is a bit string of length siglen, and share it with the client. So we're assuming that these protocol parties have a way of communicating in a way that the adversary, the attacker, won't be able to see. Server generates seek, bit string of length siglen, and shares it with the client. The third party, crucially, doesn't know it. Then what happens is main asks the environment, hey, what's the database you want us to use? So a list of elements. That's then passed to the server. The server randomly shuffles it. So it changes the order in a random way. Then what it does is it takes each element in the database, pairs it with the secret that the client also knows, takes this pair and hashes it. And that gives us a hash tag, a bit string of length taglen. So for each element in the database, we're making a pair of that element in the secret, and we're hashing that. And that's giving us a bit string of length taglen, a tag. We put all of those tags together into a hash database, which we give to the third party. So the third party, so we took the database, it got shuffled, each element was paired with seek and hashed. It's those hashes that go to the third party. And now maybe you can guess the rest, because now the environment is asked, what's your next query? the environment can say, oh, I'm just done at that point. Let's finish up the game. But if it says, oh, okay, here's another query, the client then does what? Well, it pairs it with seek and hashes that and sends the resulting tag to the third party. And the third party now says, oh, well, I have a list of tags, and I just got a tag, so I should count how many times this tag appears in the list of tags, and that should be the count that I send back to the client, and then I send back to here. So the third party is dealing with these tags. It doesn't directly know anything about what they're the hash of, but we're going to be talking about how much it could learn nonetheless about what those tags corresponded to. Let me show you an example. Oh, right, sorry. At the very end, the main driver says to the environment, okay, you've, based on what you've seen, what's your Boolean judgment? And so that's the result, and then the result gets returned as the result of the overall protocol. So here's an example. Suppose the original database was 0, 1, 1, 2, and the queries are 1, 2, and 3. Then, well, the server randomly shuffles, so maybe it's 1, 0, 2, 1. Then what does TP get? It gets a temperature warning, obviously. So the server is going to pair 1 with the secret and hash it. Suppose that gives us T2. Does the same thing with 0 and 2. But then 1, right? 1 was already paired with seek, and hash gave us T2, so this will be T2 again. And then, well, right, so those for these hashtags, and then the client 2 is going to get turned into T3, and so it's going to appear once. 1 is going to get turned into T2, and so it's going to appear twice. So that's how this protocol works. And I mean, again, let me just emphasize this. So we're not trusting the third party. So if the server and the client were trusting the third party, well, the server could just send its database there, and the client could just send its queries, and the third party could do the counting, and if you're trusting that third party, that would be fine. But here, we're trying not to minimize the trust of all three parties. And so it wouldn't be safe to send to the third party the actual elements. So we're hoping with this hashing technique that we're not letting the third party learn too much. So let's see. So I think we're going to be able to take some questions. So again, this is on, the proofs are on GitHub. There's a paper about this that I wrote with one of my BU crypto colleagues, Mayank Varia. And right, well, next time we'll review the material from today, consider the EasyCrypt formalization of the protocol and the real and ideal games for each protocol party, and then give a high-level sketch of the proof. And so in answer to a question from before, if I go back to the picture, we're actually going to have 3 pairs of real and ideal games. One for the server, one for the third party, one for the client. The real games are going to be specializations of the protocol, but where we have so instead of the environment, we're going to have a notion of an adversary, and we're going to let the adversary see everything that happens inside the execution of the party that we're talking about. So all the data that the server or the third party or the client sees, each time we invoke the adversary, we'll say, here's all the stuff, I'm bringing you up to date. You can see all the stuff that happened inside this. But then for each of these protocol parties, we'll have an ideal game that will be parameterized by a simulator, where we'll be talking about the leakage between the ideal game, the ideal functionality, and the simulator. And so we'll be able to precisely understand how much the adversary could possibly learn. Again, the adversary in this honest but curious security, it's supposed to be thinking, from the stuff that I'm seeing, I'm not allowed to actually change what happens, but I'm absolutely allowed to look at everything I see and put on my evil hat and try to think, is there more I can learn here than I maybe should be able to learn? That's what it's trying to do. But in the real protocol, the real world for each of these parties, we have to play fair in this modeling and let it see everything that it should be able to see. In the ideal game, though, we want to have this simulation-based definition where we can analyze it and think, okay, what exactly can the adversary possibly learn? So that's the goal in the ideal world. And then when we prove that the adversary only has a small, negligible chance of telling the real and ideal worlds apart, then we're indirectly saying, well, because the ideal world is secure by construction for whatever definitions we give, then we should think that the real world is as well. So that's where we're going. So let me just summarize something and take any last questions. So we're talking right through all of these lectures about the real ideal paradigm. So far, we've seen two instances. One for security of PRFs. The other was not at the top level of in-CPA security, but it was at the core of the proof. So we had the in-CPA game as the real. The ideal game was that final game in which we know that the adversary doesn't, the ciphertext that the adversary gets has nothing to do with the plain text. So that was the ideal game. So this is a simple form of real ideal where we have a real game, an ideal game. There's no simulator, but the adversary is just trying to tell them apart. That was core to what we did in the first example. But in the next two examples, beginning with this one, we're having a simulator like we did in that diagram when I was trying to introduce all of this at the very beginning. So, quick question or two? Yes?
So can EasyCrypt do proofs of computational security, like hardness assumptions and PNR?
Well, I mean, so we kind of already did that, right? So the question is, can EasyCrypt do computational proofs involving hardness assumptions? Well, the PRF assumption, right, is an example of that. And so, yes. And so that's this thing where a constructed adversary's ability to differentiate, to win some game, you know, some other game like the PRF game, that is exactly what you do in a cryptographic reduction. Let's take a question up here.
Do you have like a real-world example of where we see a setup like we have in the PCR protocol?
Yeah, I mean, so the story here, this is something that cryptographers try to do with more realistic databases. And so the idea is that they want, no one trusts, each other, and so they want to have a multi-party protocol where the trusted computing base is as small as possible. They're using crypto for that. We were working at a project at MIT Lincoln Lab to try to formalize a more complicated protocol, that was a more interesting database, but we ended up backing off and doing something simpler as an example. So you can, if you read about private information retrieval, PIR, then for in crypto theory papers, you can see what's being done with that. And I think like the government is maybe using these things. But so this is obviously like a trivial example, but at the time when this work was done, that was, it was complicated enough, and I thought pedagogically this is a good example. Last question. So you've had does someone else have a question? Oh, okay, go ahead.
So in cryptography, I think there are proofs where you assume P is not NP, P is not equal to NP, and then you prove that your protocol is secure. Can you do things like that in here?
So the way that I think of it is crypto theory people sometimes do kind of proof by contradictions. But here what we're doing is the reduction is always in the upper bound. And so anything that can be expressed in that kind of way, so maybe you can indirectly do this kind of thing, that you have a constructed adversary that is trying to do something that's equivalent to that. I'm not sure, but instead of thinking if you can break the security of this, then you can break the security of some primitive. We don't really think that way in EasyCrypt. Instead, we do the reduction so that it lives in the upper bound. So we actually have a constructed adversary trying to differentiate, win some game as part of the upper bound. And that's, I think, the fundamental difference. So we're told there's someone who's doing simultaneous translation, and we're told we should stop on time. So come up if you want to ask more questions.